Thank you for having me here today. I'm going to be going over flash graphene and how we can use the same sort of heating to make materials and how we're using it environmentally as well. And let me just start and talk about some of the topics that we won't specifically be covering today. We work in the area of splitting of carbon nanotubes. We've worked in the area of computer memory. Actually, these sort of splitting of carbon nanotubes, making nanoribbons, these nanoribbons are sold now and they're commercialized. This is a type of memory that's sold now through a company called Weebit, which has gone public. It's a two-terminal memory, ReRAM sort of memory. We started another company around one of the materials that we've made are compounds to treat traumatic brain injury and stroke. Traumatic brain injury is the #1 disabler of young adults, and stroke is the #1 disabler of older adults. And so this addresses both of those. This is growing carbon nanotubes seamlessly from graphene. And when we first made this, we saw that the surface area was about 2,800 meters square per gram. And so we knew that this would make a great electrode. And we turned it into electrodes. That's part of a battery company now called Zeta Energy, which is in Houston. This is a bottle of graphene quantum dots. When we started this work, graphene quantum dots were $1 million per kilogram. And then we learned how to make graphene quantum dots from coal, which is $60 per ton. So think about that, $60 per ton, one step, 25% yield to something that would sell for $1 million a kilogram. So of course the price has come way down, and that's sold through a company that we started called DOTZ, D-O-T-Z. One of the things that we do is we take waste plastics and we convert it into a material that will absorb CO2. So we try to take one problem and use it to address a second problem. We have another area where we work on nanocars. So you see there's 4 wheels here, and the idea is that you have this Feringa motor on this, and what happens is when you shine a light on this, this Feringa motor will activate and start spinning, and so the idea is to push the nanocar along a surface. And these Feringa motors actually spin at about 3 million rotations per second, so much faster than what you're seeing here. And you can see cars driving across the surface. We have another area where we've taken the Feringa motors, and what we've done is we've attached peptides to them, peptides that will identify something that is overexpressed on a particular cell surface, so we can direct it, say, to cancer cells, and then turn on the motors by shining a light, and then it drills into the cells and kills them. So the idea is that it drills in and pokes holes in the lipid bilayer. This is a superbacterium. Superbacteria are a real problem. They're slated to kill 10 million people per year by the year 2050. So when you students are my age, there'll be 10 million people per year dying from superbacteria unless we get our hands around how to address these things. So this is one mechanism, and we've come up with a new class of molecular machines, which we call molecular jackhammers, which actually vibrate at about 1 trillion vibrations per second, whole molecule vibration. And that's the next generation of these that we can activate with near IR light so we can get good penetration through biological systems.
If you do not believe in the physical resurrection of Jesus Christ, send me an email, tour@drjamestour.org, and we will get together and I will share with you about why I embrace the resurrection of Jesus.
This is an area that we had worked on a number of years ago, and it's become a very popular area, and it's also being used here in your department. I've met some people today that are talking about this. This is the area of laser-induced graphene. You can take any laser that's found in a machine shop that's usually a 10.6 micron CO2 laser. They're used for scribing and for cutting. You probably have a dozen of these on campus. And you can hit polyimide and turn the polyimide into graphene. But then we learned that if you just defocus the laser by 3 centimeters, what you can do is you can write on any carbon surface. So here, for example, you're not dropping graphene onto bread, you're converting the carbohydrate strands of the bread into graphene. And as fast as the laser writes, it writes this pattern. So whatever pattern you want, you can do it on wood, on a cardboard box, you can do it on paper, you can do it on a piece of bread, you can do it on a cotton shirt. Anything that's made out of carbon, you can carbonize and turn it now into a layer of graphene, and these are being used a lot now for sensors and for air filters and for water filters as well. This transitions right into what we're going to talk about today, and this is this ultra-fast heating and cooling route to new carbon materials. And so that laser-induced graphene method is using systems that are exciting in about the microsecond time range, and the systems heat between 2500 and 3500 Kelvin. And but what we're going to focus on today is not this, and we're not going to focus on this, which are the CVD routes to grow graphene, but we're going to focus right here, flash joule heating. So flash joule heating is usually done in milliseconds to seconds, so it's very fast, and you can hit an entire temperature range. You can be easily up over 3000 Kelvin. So you can heat very quickly, and it cools very quickly. And because you're heating and cooling very quickly, you can trap things in high entropy states, if you like, and make new materials that way, and we'll discuss that today. So this was a technique that was developed by a student of mine, Dewey Luong, and he found that you can put any carbon source between two electrodes, any carbon source between two electrodes. So people like to write to me, they say, well, I have a particular carbon source. Will it work with that? I'm like, yes, it works with that. And they said, well, could you try it? I said, I know it's going to work with that. And that happened with Eric. He contacted me. And I said, I know it's going to work with it. So he sent us his thermoset plastic, and sure enough, it makes graphene. Any carbon source to be put between two electrodes, you put a high voltage and a high current. It heats to over 3000 Kelvin in about 3 milliseconds. And then it heats at about 10 to the 5th Kelvin per second, and it cools at about 10 to the 4th Kelvin per second. And what happens is you're pumping in enough energy that every carbon bond in there, every bond in there breaks, just breaks. And then it's going to reassemble, and the thermodynamically most stable form of carbon is not diamond, but it's graphene. And it reassembles as graphene. And so you get a big flash of light in the process. This is black body radiation, and you get graphene. So you get these graphene sheets coming out, and this clearly nice graphene. So this is what Dewey had discovered. And if you want to see the best spectrum that's ever been published on graphene, here it is. This is the G band. This is the 2D band. It's 17-to-1 difference in height between the 2D and the G band. That's not the D band, not the disordered band, but that's the G band, the graphitic band, this little thing here. The 2D band is very large here. So it's tremendously clean graphene, and this is because you have a turbostratically stacked graphene. In other words, graphite is you'll have AB stacked generally in graphite, where you have the benzenoid ring, and then the next ring below it will be just slightly off, half a unit off, so that you have the electron-rich portion, which is the edges of the benzene ring, over the electron-deficient, the middle portion of the one below it. That's AB stacking, because it has geological time frames to be able to get in the right order. Here, it heats and cools so rapidly, you have disordered layers, which we'll see on the next slide, and that makes it much easier to separate these. And so you can see you can do it with carbon black as your source, anthracite coal, calcined coke, or you can do it with coffee. Coffee is a carbohydrate, so it's 40% carbon, C6H12O6, 40% carbon by weight. We can get 35% yield of graphene from waste food, waste plastic, whatever is made out of carbon. Most of the things you see around you, if it's not glass and it's not metal, it's carbon, including us. And you can turn all of these things into graphene this way. And so this is what AB stacked graphite looks like. AB stacked graphite, you pull it apart, you get one layer just over the next layer, so you get the electron rich over the electron deficient, but it's hard to pull these layers apart. When it's turbostratic, there's no particular adhesion between the layers. And so it's much easier now to blend these into composites when you have turbostratic graphene, and because it forms and cools so quickly, you get turbostratic graphene. We built automated systems. This was actually built during the COVID shutdown. I don't know what it was like here, but we were out of our labs for 2.5 months during COVID. So before we had to get out of our lab, I bought a bunch of 3D printers and sent them home with the students. And I said, just start building. And so they built this system. It was an automated flash joule heating system. We got all the other parts were from Amazon or eBay, because those were functioning really quite well during COVID. And it built this system. And so what we could do ultimately from this, because we had gotten a grant from the Department of Energy just before COVID in 2019, October. And we had to deliver within 2 years. We had to take a U.S. coal product and make 1 kilogram in a day. 1 kilogram in a day of graphene from that coal product. And so with this automated system, we were able to do that. And in fact, we could make the 1 kilogram in an hour and a half, where these just roll in, it flashes, and then it drops out the bottom, and another one charged would already roll in. So that was the automated system that we built. And we used AI machine learning to optimize on this. There's many parameters to turn here. So this is perfect for machine learning, where you have all these different parameters. So you have the different sources that you could come in with, and then the different parameters that you need to set, and we could analyze on this, and we could quickly tune in on optimization for graphene. So if you have a high carbon source like coal, metallurgical coke is a coal product. It's the material that's used to make aluminum, where you have a sacrificial electrode. And what you can do by building these sort of systems is when you have that level of carbon, it's 90% carbon, you can get 90% yield of graphene. In other words, if you start with a kilo of metallurgical coke, you'll get 900 grams of graphene out of this, where almost all the material in there is graphene. You can only get 90% yield because it was only 90% carbon to start with. If you start, like I said, with carbohydrates, your yield is lower, but your carbon yield is still very high. It depends on how much carbon you have going into the system. What's the advantage of flash graphene? So it's non-toxic. Graphene is non-toxic. It's even used in several medical applications. It's naturally occurring in the environment. So we're not introducing a new material to the environment. Graphene shears off of graphite in riverbeds, and so graphene has been in our environment for a long time. It's a terminal natural sink for carbon. Any asset you bring up from under the ground is going to eventually end up in our CO2 cycle. If you just make carbon and throw it out, these will be taken up by the environment, by trees, and they'll eventually turn into CO2 when those trees die. But if you turn it into graphene, it's very slow to enter the environment. And remember, you only have to slow it down by about 100 years, because in 100 years we'll have other sources of energy which are not blowing out CO2. So once you convert it into graphene, microbial decomposition is very slow, and we know that because we have graphite in the world. We wouldn't have graphite mines if microbes could eat that graphite. It can be used in composites of all types. The flash process requires no solvent, no water, and no purification. If you have silicon in there, if you have aluminum in there, those are distilling out. Silicon and aluminum are both boiling at about 2600 centigrade. This is going to over 3000 centigrade. Carbon doesn't boil out to almost 4000 centigrade. So you have a big window there, and all these other elements can come subliming out or boiling out. The electrical flashing cost, you say it must take a lot of energy. No, it doesn't. It takes about $30 per metric ton of coal, $30 in electricity. $30 in electricity. You say, well, don't you use a high voltage and a high current? Yes, but for very short amounts of time. We're not heating a big furnace, which is normally done with furnaces. You have to heat that whole system. Here we're driving all the energy right on into the material. Even when we do these small scales in the lab, sometimes you can have the inside to 3,000 Kelvin, and the outside is just warm to the touch. Because happened so fast, there was very little heat transfer to the outside. So it's all driven into the system. The current price of graphene is $60,000 to $100,000 per ton, depending on where you buy it. So that shows you that you can take a carbon source like metallurgical coke, it's $150 a ton. You put in $30 worth of electricity, you can get graphene. So that could be a good business. So we started this company called Universal Matter, and Dewey Luong, who's the inventor of this process, he's there in the company as well. And this company is targeting several early applications. What they decided to do is not sell graphene. And the reason they don't want to sell graphene, because what they found is if they sell graphene, people try it in their applications. Industries try it. And guess what? It doesn't work. Because they just throw it in like pixie dust and they expect this thing to work. And if you've ever worked on nanocomposites, nothing works that way. It's very hard because you need two things to make a good nanocomposite. You need to have good dispersion, so it has to disperse through the host material well, and you have to have good interfacial interaction. So you have to have a good interaction between the host material and the nanomaterial that you're adding. If you don't have those two things, the nanomaterial actually weakens the material, doesn't strengthen it. And so what they found is people would try it, they'd say, this doesn't work. So they only sell master batches. So in other words, if you're working with cement and concrete, you buy a bottle from them and you add this liter of material to a cubic meter of your cement. And you blend that in and then make your concrete out of that. So they sell the master batches. The same thing with asphalt. It's a complete replacement for the styrene butadiene rubber in asphalt. And by doing that, it raises the working range by 11 degrees centigrade. So I live in Houston, you live in Phoenix, and you know when it gets very hot outside, you can't have asphalt roads because trucks will sink right into that road. If you can raise the working temperature by 11 degrees centigrade without affecting the low temperature, that's quite substantial. In cement and concrete, you can use 20 to 30% less concrete. That's a big deal because concrete is 8% of all CO2 emissions by humans come from the making of concrete. You take a metal carbonate, you heat it up to 1400 degrees, you blow out CO2, that's where all that CO2 is coming from, and you're heating the furnace to 1400 degrees, you blow out CO2 to make the metal oxide. Then you take that metal oxide material and you're mixing it with rocks, and then you put it on a heavy truck with a lot of water and you deliver that to the site. All of that, 8% of all CO2 emissions. So if you can reduce that by 20 to 30% by adding 0.06 weight percent of graphene, that's a tremendous advantage. It's going into paints and coatings, it's going into rubber tires. So these are the initial marketplaces that this is going into, and they're running now at 1 ton per day production of graphene by this flash process in a pilot plant. So this is not what can be manufactured. This is in a pilot plant. So in a pilot facility, they're running at 1 ton per day. So yes, this process can scale.
Just a quick reminder, this organization is run totally by volunteers, but we do have to pay for the production work. If you could help us out by going to give.jesusandscience.org, we'd appreciate it, or you can click in the description box below. If you can't give, we certainly understand, but please just give us a thumbs up and click subscribe. Thank you.
So how is this an energy effort? Well, where will energy come from in say 20 years from now? Right now, what we do is we take methane, we combust it, natural gas, we combust it, we make CO2 and water. That blows out about 800 kilojoules per mole. So that's the amount of energy that we can get out of this. But what you can do is you can take methane and you can convert it to carbon solid and hydrogen, 2 moles of hydrogen. This process has actually been around since the 1950s. It was called furnace black, but they didn't know what to do with all this carbon solid. So what do we do today? We just blow the carbon right out into the air. Just blow it right out into the air. But this would make carbon solid. But if you throw out this carbon solid into the environment, this will be taken up by microorganisms and by trees, and the trees, it's all going to form CO2 eventually. But what we want to do is, of course, take this and turn it into graphene. Well, then you can take this hydrogen. So how do you pull these off? There's many methods. Probably the most common method now, this largest scale method, is molten salts. You take it and you run methane, natural gas, through molten salt. You'll get CO goes to CO2 and H2. And then you can take that H2, put it with oxygen in a fuel cell and make water as your only byproduct. So overall, this blows out about 400 kilojoules per mole of energy. So you only get half the energy out. But all the oil companies are switching to this. Why are they switching to this? Because if you look at efficiencies here, the top reaction is only about 25 to 40% efficient. Pulling the hydrogens off of this carbon is 90% efficient. So you have this 90% efficiency, and then the next step after this is 80% efficient. So if you just look at the efficiencies overall, it's about the same. So these two processes are blowing out about the same amount of energy for you. when you look at efficiencies. Now, normally you would have 30 billion tons of CO2 being emitted. Well, that means if you just chop off those two oxygens, that'd be 8 billion tons of carbon. What are you going to do with 8 billion tons of carbon? We want to turn it into flash graphene. What could you do with that? Well, if you look at the different building materials that are used today, everything is swamped by cement and concrete. Cement and concrete is 44,000 million tons of building material. That is much more than all other building materials combined. So what we hope to do is to be able to put this into building materials, enhance the amount of building material, lessen the amount of building materials because we're going to enhance it with graphene. How is this an environmental effort? Well, human waste footprint. 30 to 40% of all food worldwide is thrown out. Why? Because it has to be, because it goes bad. I mean, everybody's cleaned out their refrigerators. I bet you got refrigerators in this building that just have food rotting in it, and you have to throw that out on occasion. But food is particularly bad in a landfill because it blows out not just CO2, but it also blows out methane, which is a much worse greenhouse gas. There's a lot of waste plastic in the world. For those of you from Asia, you know how severe that problem can be. And rubber tires, again, a big problem around the world. The U.S. has learned to deal with this because we pay for the waste tire disposal when we buy a new tire. And so we've learned to deal with this, but it's a big problem in the world. All of these can be turned into flash graphene. So here's all the different recyclable plastics after we flash them. All of these are beautiful spectra of graphene. Recycling is a very hard way to go. We do recycling because it really makes us feel good that we're recycling. But you don't save anything from recycling because what happens is human beings stand there and separate the different types of recyclable plastics. And these are just thermoplastics. You can't do this with thermosets. Just the thermoplastics, you separate these. After they're separated, say polypropylene, by hand, this is then sold to a recycler. That is about 90% polypropylene. Then the recycler will take this, it's chopped up into little flakes, and then those flakes are washed 3 times with hot water and detergent. There's a big cost in that, both in energy and dollars. And then that material is then dropped down these transparent tubes, and whatever is not falling at the rate that polypropylene falls is blown out through holes in the tube with a puff of air, and so little flakes of aluminum, little aluminum foil, little flakes of paper, that's all blown out. And then they take that, they melt it down, and they make polypropylene. That polypropylene can never be used for food, can never be used for pharmaceuticals. And it's not as good as the virgin material, and it costs exactly the same amount as the virgin material. This whole thing about using recycling and thinking that that's a good method is not such a good method. But what we can do is we can take the entire mixture. You can take the entire mixture. You don't have to separate. So we can take this entire mixture and we can flash it. It doesn't matter. If there's chlorine in there, that's blowing out as HCl anyway. It doesn't matter. We don't have to separate these. So the cost of this, and now it's a huge upcycle because you don't sell this for the price of a plastic. You sell this for the price of graphene. All right, so what we did is we worked with Ford Motor Company in Europe right now. The car comes back to the manufacturer after the life of the vehicle. After the life of the vehicle, so say a Ford is now 30 years old in Europe. It comes back to Ford Motor Company. And they say, you have to deal with this. You can only landfill 5% of it. The rest of it, you just got to deal with. And so Ford gets this thing back, and they don't know what to do with it. You have 200 to 350 kilograms of plastic per lightweight vehicle. The metals you can melt down, what do you do with the plastic? A lot of these are thermosets and all sorts of mixtures. So we got 10 pounds of that plastic. It's from their stripper lots. Every wire is stripped, every bumper, all of these plastics. So we got all that plastic and we turned it into flash graphene. We took the flash graphene, we sent it to Ford Motor Company, Detroit. Ford took that graphene and then put it into their new composites, because since February 2020, every Ford has had graphene in it. It's in the foam cushion seats, it's in the underhood insulation, and it's going into more because it lightweights the vehicle. So they put it into their foam cushion seats. It did everything that it was supposed to do. It increased the modulus, it increased the compressive strength, and it had a better coefficient of sound absorbing. And so you can see the foam cushion seat is a little bit darkened with the graphene versus the virgin foam. So I said, give me that foam cushion seat, send it back to me. We got the foam cushion seat. Guess what we did with it? Turn it into flash graphene. And so you see now the life cycle. You can just take old vehicles, turn it into material for new vehicles, and just keep going back around. This is not taking a plastic and recycling it, where you would lessen the molecular weight. This is totally breaking every carbon-carbon bond in it and letting it reassemble. So that's how this is an environmental application. We can add different heteroatoms to the graphene. So what you can do is you can take the graphene, add these different heteroatoms to it, and then flash it. Or you can take flash graphene, add heteroatoms, and flash it again, say to 1500 degrees. And you can make these doped graphenes this way. So you see we can make boron-doped flash graphene, nitrogen, oxygen, fluorine, phosphorus, sulfur, or the mixed ones, for example, boron, nitrogen, sulfur, or boron, nitrogen, fluorine. The fluorine sits above and below the plane because it valency of 1. These other ones sit in plane, in the graphene. You can watch the evolution of this. So this is over 1 second. So we think of evolution over periods of hundreds of millions or billions of years. Think about evolution over a period of 1 second. If you take, say, carbon black and you flash it, in the first 2 milliseconds, it's still amorphous. By 10 milliseconds, this is actually where we had added, this was actually a sample of polytetrafluoroethylene, which is Teflon. We're flashing Teflon. In the first 10 milliseconds, it forms into fluorinated nanodiamonds. If you continue heating to 100 milliseconds, you get the fluorinated flash graphene. If you continue heating to half a second or 1 second, you get these fluorinated concentric shells, these concentric carbons forming. So you can stop it at any point along this evolution because you're doing it with electronics. So to stop anywhere at any millisecond time period over a 1 second time period is a very easy thing for electronics to do. It's just that our evolution time period is 1 second. If you add an iron source to this, so say you add ferrocene to the plastic and you flash it, instead of getting graphene, you get carbon nanotubes. So because carbon nanotubes form at a much lower temperature because it's a catalyzed growth, and so it'll catalyze off the growth off of those iron atoms, and you get carbon nanotubes. So we've started another company around that. The graphene market is about 14 tons per day is the worldwide graphene market, about 400 million a year, and this is going to go way up as we get more ways to lower the cost on this. The nanotube market is 15 billion a year. So there's a lot of multi-wall carbon nanotubes being used. So it's a good market. It's a good way to take waste plastic and throw it right on into some important application here. What does the electric field do? Well, there's been a number of publications. All of these are publications from the literature suggesting that an electric field can change chemical reactions. You can lower activation energies with electric fields. So we wondered, is this a thermal process or is it electrothermal, meaning the temperature plus the current going through the material? And plus, does a kilohertz pulse, because we're often using kilohertz pulses through this material, does that affect the morphology? So what we did is we built two different systems. In one system is our traditional system where you put material between two electrodes. And then we are driving current through all the material. The other system is we take a carbon paper, which is conductive, and we put our material right on top of it. So most of the current is going to go through the conductive paper, not through this material sitting on top of it. Will that affect things? Well, it does tremendously. So if you look, you put in 100 volts through this, so you look at the temperature versus the time. The temperature here in this sample hit 2,000 degrees. If you look at the material, you get very little graphene. You don't see a big 2D band at all. This looks almost like an amorphous carbon. But if you only put in 80 volts here, you can hit 2,000 degrees and you get very nice flash graphene. Very nice flash graphene. So even at a lower voltage, when you're driving a current, you're getting good graphene on this. And again, this is shown in the TEM, and in the X-ray diffraction. You have amorphous material, here you have good crystalline material, and by the XRD, good crystalline material. If you look at the comparison, so this is still 120 milligram samples in both of these reactors. If you just do it thermally, flashes at the same energy, you get, here's the graphene yield. This is what you get. It's sitting on top of a carbon paper. This is what you get if you're driving a current through it. So it is truly an electrothermal process, not a thermal process. If you want to get flashes with similar product constituency, this you have to put in thermally 19 kilojoules per gram. Here you put in 4.2 kilojoules per gram. And here you can look at the electric field and what happens when the electric field starts increasing through the sample, you get better and better graphene. So what we can show here is you can look at the different activation energies. So you take metallurgical coke activated carbon, and if you do it thermally, you have to put in 410 kilojoules per mole to get it to go to turbostratic flash graphene. Graphene is more stable than amorphous carbon, so you're going down, so delta H is negative, your enthalpy is negative, though you had a high activation energy. And then from turbostratic to graphite to where you really get a graphitic material, you have to now order these different layers. You have to pump in a lot more energy, 1640 kilojoules per mole. Well, on the same amount of material, here you're putting in half the amount of energy. So you've really lowered the activation energies by driving a current through the material. And here's our simulations. Now, when you go to a 5.7 gram of material versus 120 milligrams, the activation energies are lower, which just tells us that we're losing a lot on a small scale. The amount that we lose of heat content here and energy content is we get a lot more loss than when we're using a big sample. And this is the same thing we found when we've gone up to scaling this to much larger commercial processes. The amount of energy that you need to pump into this is less because we're not losing as much to the environment. You can see the same sort of thing at 40 volts. It's amorphous. At 80 volts, you start seeing the graphitic layers here, the graphene layers. At 120 volts, it starts forming much better. At 160 volts, you got graphite. You see the nice ordering of the graphite, and the distance between the stacks tracks with this, and so does the X-ray diffraction. So you can see that this is really a process where by energy content you can control the type of material that you're going to get. We've looked at the current oscillations. So if we have this 60 hertz pulse, you don't have to put in as much energy, as much large energy. So if you get something that looks a little bit more like a square wave, and so here's what this duty cycle looks like if you expand on it, this actually helps the material to order in this way. And you can see what happens is if you have 100 volt with duty cycling versus just 100 volts, you get a sharper Lorentzian here, so you get a cleaner material. Here's 100 volts, here's 100 volts, duty cycle. This is the peak height of the 2D, reflective of the purity of the material. You get a much better material with these duty cycles, and that's exactly what we had modeled. This is the simulation, so when you don't have a duty cycle versus you do when you have the duty cycle, that helps these sheets now to order and arrange. So just the typical pulsing, the 60 hertz pulse is helping the system. So you may say, well, okay, that's a great technique for your lab because you built all these big flash Joule heating apparatus. Well, it turns out the Chinese companies have started making these flash Joule heating apparatus, so you can buy them. But you don't have to buy them now. We've just shown now that you can use a $125 arc welder from Amazon. You just buy an arc welder, it's about the size of a shoebox, and you can do this. We bought this $180, little bit higher-powered arc welder we got from Home Depot. Or you can use these Variacs, or you can use a direct current power source, or you can use actually even a much bigger system here. This is often found in chemistry labs. All right, so if you just look at the different reaction systems, the cost effectiveness per reaction type, clearly an arc welder is the way to go, or the most economical per dollar unit to use. This flash Joule heating system 5 is our big flash Joule heating system. This was some other systems that have been made, but all it takes is an arc welder. And what we found is you can just take the arc welder and go to the current setting, which is not really a direct current setting on the arc welder, but it's close enough. And just by turning the dial, you increase this, you get about these small increments. So just as you start increasing the dial, you can dial in the temperature. Here's 1100 degrees up to 1600 degrees. So you can either use a high temperature flash or run it a little bit longer with an arc welder. And so you can see that as you dial this up, the material just starts heating higher and higher. And through this, we took that little $125 arc welder plus $50 in electrode supplies, just 2 carbon electrodes, and you can make very nice flash graphene. It's turbostratic, which you can tell by the TS1 and TS2 bands in the Raman spectrum, and you can make very clean flash graphene. And if you add an iron source, you add some ferrocene to that. Instead of making graphene, what you end up making is you make the carbon nanotubes. So you get the carbon nanotubes here just by adding iron. And then, interestingly, arc welders are inherently pulse width modulated. They are inherently giving you that pulse, that pulsing that actually helps in the building of the systems. Now, here's the flower pot method. You just go and you buy a flower pot. Flower pot is made out of clay, and so it can handle these temperatures. You just take metallurgical coke, put it in there. Metallurgical coke is $150 per ton. 2 carbon electrodes and an arc welder, and you get graphene. That's all it takes. Just do this in the hood, and the fumes are just blowing right out the hood. And so here's the scaled system, and you can just take this flower pot and you just stir it around with the arc welder going. We bought a little turntable from Amazon and put this on there and just start spinning it around. And this system produces 3 kilograms of graphene per hour. 3 kilograms of graphene per hour. So you can make all the graphene that you need for your lab for $125 arc welder, and well, this one we used the $180 arc welder and a flower pot and a spinning platform and 2 electrodes made out of carbon. That's it. It's all you need to do this in your own lab. And so when we look at the price here, we took 2 of these arc welders and we put them in series. You can put them in series and you can increase the production rate to 5 kilograms per hour or 0.12 tons per day, just in your lab with an arc welder. And so if you look, this was the procedure that we had published from that DOE grant. When you look at the price versus the production rate, and this is a logarithmic scale in price, and here it is with 1 arc welder, here it is with 2 arc welders, and the production rate, and so you can see this comparison. If you look at the production rate in kilograms per hour and energy efficiency, this was a paper that just came out this year from China of a method to scale the system versus what we can get with just 2 arc welders put in series. That's all it takes. All right, what about the rest of the periodic table? We've talked a lot about carbon. So for the rest of the periodic table, we have this flash within a flash. You have to get conductive materials. So when you use plastic, plastic's not conductive. We're running a current through this. So how do we get it conductive? We'll add 10 or 20% by weight metallurgical coke to that waste plastic, and that's enough to give us enough conductivity to flash this. But say you don't want carbon around, because if you have metals with carbon, you often get the carbides, and we published a whole paper on metal carbides. Well, what we decided to do is if you didn't want to have carbon around, you put your inorganic components in an inner tube, cap it, and then put an outer tube around it. You put this outer tube around it and you flash the outer tube, so there's no carbon on the inner tube. You flash it, you have to run it like 2 to 5 seconds. You have to run it longer because now you have to have heat transfer into the inner tube, and you make your materials in here that have never seen carbon. And so here's all the different products that we've made. We've made titanium nitride, titanium selenide, iron sulfide, cobalt sulfide, and so on. So we've made all of these different materials. We've made 22 different materials were synthesized. We've made non-sulfide, non-selenide materials. We've made a number of 2D materials, these transition metal dichalcogenides, these TMDs. So you see all the different materials that could be synthesized. And these are really clean materials. So for example, here's the characterization of a lot of materials. You see how clean these can be, and this is all in aberration-corrected TEM. And you see how clean the materials can be. And also here's commercial, for example, here's commercial molybdenum selenide. It always has a thick amorphous layer around it. Here is the flash within flash molybdenum selenide. There's almost little to no amorphous layer here. If you look at this, you have this atomic pattern right up to the edge of the material. So it's really a different material, and this is why we see these amazing properties. So it's a one crystalline orientation, it's no polycrystallinity, and no amorphous layer. To get one little chip, one of our reviewers said you're going to have to compare it to commercial material. We had to pay over $600 for a tiny little crystal of commercial material, and we were making grams at a time in our lab using this methodology. So it changes the access to materials throughout the periodic table using this kind of methodology. And if you just look at the life cycle assessment, if you look at the megajoules for 100 grams, here's the flash within flash, here's the amount of CO2 you're going to make, the amount of water that you need, and then the preliminary production cost. So you see that this is a much better way to go. What about environmental and waste management applications? So how can we extend this to other things? Well, if you haven't heard of PFAS, you're going to hear about it now. PFAS is per- and polyfluorinated alkyl substances. This is in all of your blood. If you here in the United States, it's in your blood. It's in fetuses, it's in women's breast milk, and now they're finding that this is affecting our immune systems. PFAS has been used. There's over 14,000 products now, 14,000 different PFAS materials have been made, and it's spread ubiquitous throughout products. Teflon is a PFAS material, polytetrafluoroethylene. We cook on it. Every time you go to McDonald's, have you ever gotten French fries in that little paper container at McDonald's? Isn't it interesting that that paper container doesn't get an oil blotch on it from those French fries? You ever wonder why that was? PFAS. There's PFAS on the inside of that container. It's sprayed in that container. Now you put your French fries in there. And so oils and water don't absorb on this fluorinated material. And so we eat it, it's been in our foods, and it's gotten into our food system. It's in our fresh water. It's in our fresh water system. I have read and been told by the Army that eating one freshwater fish in the United States, one freshwater fish, is equivalent to 1 year of drinking tap water in the United States in PFAS accumulation. Because the fish becomes the filter, and then we eat the filter when we eat the fish. You can get PFAS out of water fairly well by using a carbon filter. Carbon works actually quite well. And you can remove the vast majority of these water-soluble PFAS compounds from water. So here's what the PFAS compounds look like. You use activated carbon. So what do you do with the activated carbon now that it has PFAS on it? That is currently incinerated. There's a cost to that. Well, what we do is we add calcium hydroxide to it, or sodium hydroxide, and we take that and we flash it. All of that carbon turns into graphene, and the fluorine turns into calcium fluoride. Calcium fluoride is the natural mineralized form of fluorine in the environment. It's non-toxic. And so you can get graphene plus calcium fluoride. Or if you add sodium hydroxide, you get sodium fluoride, which we add to our toothpaste. It's a sellable material. So what is our cost to do this? Our cost to do this is minus $1,900 per ton. It's like, how can it be minus? Because we sell the graphene. But we're not selling the graphene at $60K per ton. We are selling it, we artificially lowered it to $3,000 per ton, just saying eventually it might get down to the price of a typical bulk plastic, $3,000 a ton. At $3,000 a ton, we would be making $1,900 a ton to get rid of this material. So people will pay to get this off their hands, and then we can turn around, flash it, and sell it, and still make $1,900 a ton in the flashing cost. So this is a way you can use it. What about wind turbines? We all love wind energy, right? Wind turbines are made out of a mixture of glass fiber reinforced plastic, or you'll have carbon fiber reinforced with glass. These are buried whole because we don't know what to do with them. Same thing with old retired aircraft, buried whole. Well, we can flash this. We just grind it up and flash it. We make silicon carbide. If you add iron, you get silicon carbide wires. You can add this to concrete. At 0.1 weight percent addition to concrete, to the cement, you get a 69% improvement in the flexural strength, a 57% improvement in the modulus of elasticity. So you see these effects here, so you can make new materials and use this in an environmentally nice way. Well, when you flash, say, polyethylene or polypropylene, there's 2 hydrogens for every carbon atom. What happens to those hydrogen atoms, I wonder? Well, you turn that carbon material, that polyethylene, polypropylene, you turn it into graphene. What happens to the hydrogens? It comes out as H2. Why doesn't it come out as CH4? Well, it turns out the hydrogen-hydrogen bond is about 22 kilojoules per mole stronger than the carbon-hydrogen bond. That's one reason. And another reason is the carbon is carbonizing. So if you use polyethylene, you see the largest peak here is hydrogen. It mostly comes out as hydrogen. You get a little bit of methane, ethane, and then higher C3 to C5 compounds. Polypropylene, if you have oxygen in your polymer, say in PET, you see some CO or CO2. So you see all of this hydrogen comes out. So when you look at this, when you flash this waste plastic, here's how hydrogen is normally made. Here's all the different routes. The way it's normally made is this gray route. Gray route is you take methane and you do nickel reforming on it, the steam nickel reforming. You take a nickel catalyst, steam, and methane. You heat that up and you get CO, then CO2, and H2. So if you feel good about using your hydrogen fuel cell, don't feel good about it because you've made all the CO2 back at the factory. You're just not blowing it out of the back end of your car, but you've already made it at the factory. But now you can feel good about it because now you're getting H2, which is a fuel source, not just an energy source. Sun, wind, that's energy. Fuel is something you can put in a bottle. You're generating hydrogen in this process. So while you're making graphene, you're generating hydrogen, such that the hydrogen cost for us is minus $4.30, minus $4.30 per kilo. Minus $4.30 per kilo. The DOE had a program. They wanted 1 kilo of hydrogen for $1 in 1 decade. We delivered not for $1, but for minus $4.30 when we sell the graphene at 1/20th of its current price at $3,000 per ton. So you can generate the hydrogen that you can use to generate the electricity to power your company. What about purifying the ground? We can flash the ground. We can heat the soil to 1,000 degrees. We can pull out heavy metals we'll distill out. We can pull out PFAS, carbonizes, and the fluorine mixes with the calcium that's filled in the soil anyway to give the natural mineral form calcium fluoride, and other carbons will mineralize and will mineralize to graphitic material. And you say, well, the soil must be no good. Actually, you get 20 to 30% higher germination out of the flash soil, and you get most of the nutrients. You get an increase in exchangeability here because they've been heated and they're free for nutrients. And you get all the insects die. Every microbe in there dies. But they readily reinfiltrate, and that's what we've shown. And so if you look at all the different materials here, all the different ways of purifying soil, we don't have to remove any of the soil. The soil is all in place. And so here's this. Here's our method here versus all the other methods in the cost and the treatment. So you can see what we can save here in this treatment. All right, we've recycled battery anodes this way. The anodes, usually people throw that out. That's graphite. Graphite, though, battery-grade graphite is $10,000 per ton for natural. Synthetic, which people prefer, is $20,000 per ton. We can recycle all of that. And then we can also do the cathodes this way. And all of this has been licensed out. Here's a way now, instead of just bringing out all the metals, how can we selectively bring out one metal, then the next, then the next? So DARPA approached us. They said, look, we have all of this electronic waste. We go all over the world mining. We make all these devices. We use the devices, then we throw them out. Printed circuit boards. Every time you save something to the cloud, it goes to a printed circuit board somewhere in some server farm. Those printed circuit boards are retired every 3 years. Those are toxic waste. How do you get the metals back out of them? And so if you look at boiling points, iron oxide is 3,400 degrees C. Iron metal is 2,800 degrees C. Iron chloride is 315. If you can make the chlorides, you can distill very easily. Titanium oxide, 2,900. Titanium metal, 3,200. Titanium chloride, 136. And so what you want to do is want to convert these to the chlorides. So what we do is this. We built these reactors. We built a 1-inch tube, a 2-inch tube, then a 3-inch tube. And what we do is we convert them to the chlorides. We flash them under a chlorine environment. And we look at the free energy of formation of the metal chloride. And we capitalize on that. As soon as we form the chloride, it distills out. So for example, we took tantalum capacitor waste. So DARPA asked us to find a way to get indium, gallium, and tantalum. So we did all three. And so here's tantalum capacitor waste. They look like little pieces of candy. You get this from eBay for almost nothing. They're retired tantalum capacitors. You grind it up, you heat it up, you just burn away all the carbon that's in there. You get the tantalum that's there. Then we take that with other metals, so it has a number of other metals. So we get the tantalum oxide after calcination, silicon oxide, copper oxide, iron oxide, nickel oxide, and manganese oxide. And now if you just do a direct chlorination, you heat them up with a flash Joule heater, just the thermodynamics, this is just the modeling, it's very simple on commercial software. When delta G is less than 0, it's a favorable reaction. Silicon and tantalum don't chlorinate directly at any temperature along this profile. Whereas all the other metals there, if you do the flash right here at about 1250, all these other metals are going to chlorinate and come distilling out. And that's going to leave just silicon and tantalum. Here's silicon and tantalum. But now if you do a carbon chlorination, you add carbon plus chlorine, the carbon reduces now the metals to the metal 0, and that then reacts with the chlorine and forms the metal chloride, and they'll distill out. Now, it looks like tantalum and silicon, though, are both negative delta G at carbon chlorination conditions. So what you have to do then is you have to stop the modeling, go in the lab and test this and get the Arrhenius plot, and you look at the activation energy. So the activation energy for tantalum is 31 kilojoules per mole. For silicon is 53 kilojoules per mole. So we should be able to carbochlorinate this before we ever hit the silicon. So that's exactly what we do. We take the tantalum capacitor, we flash Joule heat at 1300. All of these metals distill out as the chloride, leaving just silicon and tantalum. We take that residue, we add carbon, and we flash it. That forms tantalum chloride. Silicon oxide is the residue. Tantalum chloride comes distilling right out. Then you expose it to air, it goes back to tantalum oxide. And that's the separation. So how well did that work? What we got was 95% purity tantalum in 86% yield in whatever tube size furnace we went to. So it worked, and here was the delivery to DARPA. You know, DARPA has milestones for you. We delivered all of those milestones, both on the production rate and the purity. So we did the indium from indium tin oxide screens. We did tantalum from capacitor waste, and we did gallium from LED waste. And we hit all the DARPA goals on that. The other thing is lithium. Lithium is a very big deal. We are just hungry for lithium. And lithium is coming mainly from brines. And brines will be about 1% to 2% lithium by weight. And these brines go into these big evaporating pools, and you evaporate them, and then you separate out the lithium. So there's this big drive to get lithium. Well, you can take an ore, it's called sputamine. Sputamine is lithium aluminum inosilicate. It is about 5% lithium by weight. So what you can do is you can just look at the thermodynamics. Aluminum and silicon should not chlorinate. You should form lithium chloride right here at about 520 degrees. Lithium chloride should form when you flash under chlorine. Lithium chloride distills out at about just over 1500 degrees. So just heat your reactor, flash your reactor to about 1550. You should get lithium chloride, and it distills right out. And indeed it does. So we can distill out lithium chloride. We can get a purity of about 95%. We can get a yield of about 95%, 92%, something like that, directly out of a mineral that is all over the United States. All over the United States. We have access now to lithium in large quantities. Red mud is this leftover that's left over after making aluminum. Big problem all over the world, not so much in the US, but in Europe, in Asia, and in the Mediterranean. This is the residue that's left over after making aluminum. This is the residue. Why is it red? Because it has hematite, iron oxide. And there's so much iron in this, it's not worth going after the remaining aluminum here. So here's what it looks like. Here's the red mud, and here's the different elements that are there. You see it has so much more iron than it does aluminum in it. And so what we can do, though, is we can flash this, and we can remove the iron from this. So all you got to do is get rid of the iron, and then the normal ways can just pull that aluminum out, and that's indeed what we do. Here's the normal route to try to do this. All of these different steps. We have one step. We take the red mud, we flash joule, heat under chlorination, and all of these come distilling out. That leaves aluminum, a little bit of titanium, and a little bit of silicon, and that's it. And then you can just do the standard methods to pull your aluminum oxide right out of that. And so you can see the effects of this, that you had high degrees of iron, and you remove it so that you only have about 5% of iron left in the material. So, in summary, we talked a little bit about the laser-induced methods, and then we focused on flash joule heating. This opens up for us a synthesis method that is very rapid and allows us to get access to the entire periodic table of new materials. And it's done from milliseconds to seconds, and now the price is lowered to something that everybody can afford to even do in their home. There's nothing stops you from doing this in your home. You might want to do it in the backyard because there's some volatiles that come out, but a commercial arc welder and 2 graphite electrodes, that's it, and a flower pot. With that, we've set up a number of different companies from our lab in the past 9 years, but it's these companies in black which have all focused around the flash joule heating method. So we're just starting one company after another on this flash joule heating, and it makes much better sense to start a company than it is to license this to a big company. If you license to a big company, I assure you, you will make nano dollars. And there are multiple reasons for this. But if you start your own company and then sign joint ventures with big companies, you have 2 ways to have a liquidity event. Either you have an IPO, or what you do is the big company buys you out. And there's the big liquidity event. So that's the much better way to go. And with that, there is the group. Those are the folks that are actually doing the work. And this was funded by the Air Force, by the Army, and by DARPA. And I'll just stop there and open it up for questions. So what I will do is, after you ask your question, I'll repeat the question so we can get it on camera and hear it. Yes?
Dr. Tor, amazing talk. Wholly pleasure to present your cause. One question I have, that maybe is 2 questions. So you have all these other elements in your precursor, starting material, right? And how come they are not, for example, mainly the graphene, they are not doping the structure as a, or is there a way that they can control the voltage current to actually do the synthesis in parallel the functionalization or doping, so we can actually use the graphene for cardiac adaptation?
Right. So the question is about doping. Do all the other heteroatoms distill out when you're making the graphene? So there's 2 ways to do this. So first of all, when you flash graphene and you go up to, say, 3200 Kelvin, most other elements distill out. Not all, but most. Certainly what you find in coal products are gone, silicon and aluminum being most of those, and those are distilling out. You will have trace other elements in there that might not distill out. But you can bring it up higher. Carbon's like the highest at 4,000. These other things you can distill out, and you can hit 4,000. So you could do that. And then what we would do is we would add the other, if we wanted to make flash graphene, the first way we published it is we would add, say we wanted sulfur dope. We would add a lot of sulfur, flash it, most of the sulfur would come out, but you'd be left with a little bit of dopant. But then we learned there's a much better way. Just make flash graphene, so there you're up over 3,000. And then what you do is, after you've made that, you add sulfur. And now flash it quickly at 1200. That's enough to get the sulfur atoms to insert and have plenty of sulfur there. So we call it reflashed, sort of like refried beans. I mean, you flash it, and then you flash it again at a lower temperature, because you don't have to make graphene anymore. You just have to hit a temperature where you can do the insertion. And that's what we found works very well with boron, nitrogen, oxygen, sulfur, and fluorine. Okay.
Can you actually introduce functional groups? Use like this same methodology, maybe, the surface of the graphene? I don't know, you listed a lot of applications like cement, asphalt, gaping, coping, and things like that, but for all of them you have to do some sort of interfacial engineering on the graphene surface. and a lot of probably punctualization on the surface to make them compatible with the matrix. So is it possible to, other than docking to the crystalline structure, actually just change the surface chemistry?
Well, fluorine certainly is functionalizing on the surface. So that's functionalizing. So the question is, can we add functional groups to the surface using flash graphene? We've not spent a lot of time doing that with a lot of diverse groups, but the way we've done this when we put it in cement and concrete, we're not going through a second functionalization step. We just mixed it with surfactants. So, for example, there's a surfactant it's polyethylene oxide, polypropylene oxide, polyethylene oxide. It's used in the oil industry all the time, and I think it's F107 it's called, and and we use that, and then we can disperse it in water. I don't know what the company is doing, and I really don't, because I keep myself separated, or else I have all sorts of conflicts of interest. And I don't know if they're functionalizing to get their master batches, or if they're just doing some surfactant. The functionalization adds a cost, but there's a good chance that you could just take your graphene, add some functional material, and then flash at, say, 200 degrees and get some attachment on there. But we do know that, if you get too high, those carbon groups have a tendency to blow off too. So you'd have to hit the right temperature, but that's a good suggestion. Somebody can explore that. I mean, everything that I've said here has left a ton of stuff for other people to fill in with. Yes?
I have a question about, because by training I'm pre-manufacturing, I'm a manufacturing scientist, so I'm curious about that when you scale up, not only about like you are going to produce more materials, but also what about the consistency, like the impact into tools, like the electrode you're using, like the glass tube you are using, are they impacted by one or multiple times of processing, or how those being considered in the like scale up production in future?
So the question is on the scale up, how about those glass tube reactors? Those are actually quartz tube reactors. Those are not used for scaling. That's purely laboratory. All the companies have figured out other materials to use other than quartz tubes. And so none of those designs don't translate to the industry. We will use those quartz tubes once, and we throw them out. You can wash them, and you can certainly do that. My students just order new ones. This is the cost of research. But in the industry, it's not done that way at all, and it's all different materials that are used for all those reactor designs. So, and I can guarantee you they're not throwing out anything between flashes. Yeah. Yes?
I have a question, like you're showing a lot of materials that you're using for flash reading. So when you start with a new material, you must have to optimize the conditions for visualizing like the voltage and the current. So supposing we don't have AI to help us, how would you go around to optimize that without you're starting with a new?
So when I said AI was helping us, I meant AI helped us a lot for that paper. In reality, we don't. So AI is only good when you give it a lot of data points. And so when you start with a new material, say plastic, you start with a new material, the flashing conditions have to be different. So you have to do a lot of different experiments, and you have to give the results to an AI system for that to optimize even more on that. So by the time that we've kind of optimized on our system and come up with the data points that we need to feed into AI, and AI really likes at least 100 data points. The more you have, the better it's going to do. You already know. That's not true for industry, where industry really wants to tweak and optimize much more than we do for a paper, because all we got to do is publish a paper, and so we're okay with that. So we normally know that, so I just encourage you to just go in. I think within 10 flashes, you're going to know, okay, this is about the temperature that I need. So you can get pretty well in, say, 10 reactions on optimization for this in reality. But the other thing is, if a company is dealing, like one of the things, we have papers on municipal waste. We can take municipal waste, flash it, turn it into graphene. It works very well. And municipal waste, though, changes. You have more paper, cardboard, you have other sorts of waste food. What you can do, once you have a lot of systems in there with AI, spectroscopically, it's defining what's coming into the system now, and that is telling the AI system, and then your system is recalibrating for the feedstock that's coming in at that moment. So when your feedstock is heterogeneous like municipal waste, this will be very good. An AI system to tune this, but that's more needed on the industrial side and not for the laboratory side. Yes?
Yeah, I'm very impressed about the scale that you're making for the recycling, but I do have a question about the uniformity you're doing the flash heating. So, for example, if you are making like a kilogram of carbon or some recycled material inside a seal container or two, when you're giving a certain voltage to it, it might have different temperature because of the defects present in different locations. How would you keep the temperature consistent or to your ideal conditions?
Right, so the question was inhomogeneity in the material that is flashed may cause differences. So what we do is we make it homogeneous. So we put it in blenders, we blend it all together. The easiest thing to do in industry is chop things up. You buy commercial choppers and it chops everything up. And then if it's not a conductive material, like municipal waste, then we add some conductive material. Usually we like to use metallurgical coke, and that's all blended in. So it becomes homogeneous throughout the system. And it's actually, when you have non-conductive material, it's actually the points right between those granules, and we don't make it very fine. They're like the size of BBs or something. And it's right between those two that you get the hot spots. So there's certainly regions that are hotter than other regions, but that's spread throughout, and we're seeing homogeneity in the products coming out. Now were times early on that we would see different things from the inner part of the tube versus the outer versus the edges, because right in the middle it gets the hottest. What's furthest away from the electrodes get the hottest because the electrodes are heat sinks as well. So always when you do flash Joule heating, if you flash Joule heat, say a carbon filament in a light bulb, that thing, or a metal filament, it always breaks right about in the middle, never near the electrodes, because those are the heat sinks. So there is hotter temperature right in the middle, and we used to see differences. We see less differences now, but you can see some of that. You do see some differences. We're probably going to have to wrap it up and let the next class in here, but thank you.
If you're enjoying this series, give us a thumbs up and click the subscribe button, and that way you'll hear when we're coming out with new videos. There are no salaried employees in this organization. All the accounting, all the legal work, that's all done by friends of mine. The only thing that I have to pay for is the production work, and if you could help us out with that, I'd appreciate it. There's a link below where you can just click on that and help us in several different ways. Thank you.